Welcome to an introduction to sampling with measure transport. My name is Max Ramgrava and I'm joined in person at the conference venue by Matthew Parno. We'd also like to recognize our co-authors Ricardo Baptista and Paul-Baptiste Rubio, who helped preparing the presentation and the exercises, as well as Professor Yusuf Masuk, who has mentored all of us at various stages of our careers and has developed a lot of the research that we're about to present. Now, transit methods are a very powerful and versatile method with a lot of applications in a wide range of areas. This ranges from generative modeling over density estimation up to Bayesian inference. To show some examples for each, a study of our colleague Ricardo Baptista, for example, learned the distribution underlying the MNIST handwritten digit dataset and could then use these transit methods to generate new realizations of these handwritten digits. And uniquely, because he used triangular transit maps, he could even regenerate digits which were partially masked. That's a form of conditional sampling we will see later on in the workshop. Then, transit methods can also be used for density estimation. So if somebody provides you with a large collection of samples which you believe follow some underlying distribution, transit methods can be used to derive the accompanying PDF indirectly. This is very useful because it works even in high-dimension settings in which, for example, kernel density estimates are no longer valid options. And finally, related to generative modeling, triangular transit methods specifically also have a lot of application in Bayesian statistics because they allow us to sample conditionals of the underlying distribution. And you might recall from Bayesian inference that the object of interest, the posterior, is only one such conditional. So we'll see some examples of this in the rest of this presentation and later on in the experiments. Now, fundamentally, transit methods seek a function which transforms one density into another. And if this function is monotone, we can also invert it so we can transform both ways, from one distribution to another and back again. In this workshop, we specifically talk about efficient ways to find such transform maps. And the two distributions we will consider are a target density, some complicated distribution of interest that we might only know indirectly, either through samples or to proportionality. And we want to find maps which transform this distribution into a much simpler user-specified reference density, eta, for example, a standard Gaussian. So if we have found this map, there's a lot of really interesting things we can do. For example, we can generate new samples from the target by sampling the standard Gaussian, which is cheap and easy to do, and then applying the inverse map to transform these samples into new samples from the target distribution. That's a form of generative modeling. Now, fundamentally, all transit methods are based on the change of variables formula. If you're unfamiliar with this equation, it effectively tells us what happens to a random variable x associated with a certain distribution if we subject it to a smooth and monotone transformation S, which transforms it into a new random variable c associated with a new PDF. And this change of variables formula tells us what this new PDF effectively looks like. As a visual example, if we transform a Gaussian distribution with an exponential function, we get back another PDF, which is slightly slanted to the right here in this case. And the change of variables formula effectively acts in two parts. The first part maps the density, and the second part corrects for any spatial stretching or thinning this transformation might induce, which is important to ensure that the PDF that comes out of this is still a valid probability density function. Now, this equation effectively has three unknowns that we can vary. The first one is the starting distribution, in our case, the target PDF. The second one is the output distribution, in our case, the reference PDF. And the third one, of course, is the function which transforms one into another. And for transit methods, we assume we target in the reference distribution to be fixed, and we seek the function which connects the two, which maps from one to another. Now, in principle, there are infinitely many such maps which can transform one distribution into another. But we specifically consider monotone triangular transit maps, which look a little bit like this, where the full map comprises of a number of map component functions, where the first map component function only depends on the first entry of a target vector, the second map component function depends only on the first two entries of a target vector, and so on until the last map component function depends on all entries of a target vector. And to make sure this map is monotone, we force all of these map component functions to be monotone in the last argument. So S1 has to be monotone in X1, S2 has to be monotone in X2, and so on. And this structure, also known as a Knof-Rosenblatt rearrangement, has a number of very useful properties for the applications we'll consider in the experimental section later on. First of them, triangular transit maps are actually unique. So between any two given distributions, there's exactly one map which maps from one to the other for a given parameterization. A second advantage is that these triangular transit maps make it very easy to evaluate the determinant of a map's Jacobian as the product of its diagonal entries. This becomes very relevant later on when we get to optimization. And the third really interesting property is that triangular transfer maps are very easy to invert. We will see why in a little bit. Now that we've vaguely defined how the structure of our maps looks like, let's talk about how we actually find the map from the target density to a reference, or the other way around. And there are two ways to find such kind of maps depending on which information we have about the target. If we only have samples from the target distribution or realizations of it, then we can define a map which takes us from a target distribution to a reference. We call this map S. And we find the specific map by maximizing the likelihoods of a pullback density over the samples we have from the target. The pullback density effectively is the approximation to the target distribution we get by applying the inverse map to the standard Gaussian reference. So to visualize this, starting from a standard Gaussian, we seek a map which transforms the standard Gaussian into a distribution which maximizes the probability density of the samples we were given. So it basically molds this distribution to the samples. And if we then insert the change of variables formula for the pullback density, we can derive an objective function which you can split into independent optimization objectives for each of the map component functions, which are very easy to evaluate. And a large advantage of this approach is that we can optimize a map in parallel. So we can optimize each of those map component functions independently. If, on the other hand, we don't have samples from the target, but we have access to an anormalized density of a target, then we can choose a different optimization strategy where we actually define our map to act the other way around. So now our map T maps from a reference to the target. And here the optimization objective we solve is again very similar to before, but now we want to optimize the likelihood of a collection of samples from a reference, so samples from a standard Gaussian, which are cheap to generate, over the pullback of a target. So that's an approximation to a standard Gaussian reference we get by applying the inverse map to the target distribution. As an animation again, this looks a little bit like this, but we try to deform our, in this case, spiral distribution into a standard Gaussian, which of course maximizes the likelihood of Gaussian samples. So that's exactly the opposite of the example before. And once more, we can insert the change of variables formula to derive now one batch optimization objective, which depends only on the normalized density of a target, up to a normalization constant. So the difference here is that we can no longer optimize the map component functions independently, but we must optimize them together, which is a slight difference to the example from before. Now that we've sort of described what the map looks like and how we actually find the map from one distribution to another, let's talk about how we actually make it computationally tractable. So you recall that's a triangular structure, but we haven't defined what these map component functions actually look like. In principle, they could be infinitely complex, but to make this numerically tractable, we parameterize them somehow usually with a finite number of basis functions. For example, here I chose power functions up to order 2. Now, we recall from the beginning that we want these map component functions to be monotone in the last argument to ensure that the map is monotone and invertible. And unfortunately, arbitrary combinations of basis functions will not generally be monotone in the last argument. And it would be very nice if there would be a trick that allows us to convert these combinations of basis functions into something which always fulfills this property. And one very useful trick to do so is to use integrated rectifiers. Don't worry about this equation up here yet. We'll take a look at this figure down here first to explain what's going on. So assume that you start with a, in this case, one-dimensional combination of basis functions here in blue, which is not monotone. We can then monotonize this in a number of steps. The first one is we take the derivative of this basis function, which gives us this red curve here, which still isn't monotone. And if we then subject this to some rectifier g, which is some kind of function which transforms something that's positive and negative into something which is strictly positive. This could, for example, be a soft plus function or an exponential. This then yields this yellow function, which is still not monotone, but it's now strictly positive. And if we then integrate something which is strictly positive, we get back something which is strictly monotone in the last dimension. And this term up here just means that we only have to apply this procedure to basis functions which depend on the last argument of a map component function. All previous arguments can be as non-monotone as they want to be. And this then yields basically this map component function down here, which is monotone in the last argument, where the basis functions previously were not. So quite an attractive and useful method to achieve this. Now let's continue talking about triangular transfer maps. Assume now that we have defined our transfer maps, we have optimized them, and now we want to actually apply them. We want to map from a target to a reference. Now in this case, an application of a forward map is very simple. We can just evaluate all of these map component functions independently, even in parallel, and then assemble the samples from the reference density by basically just concatenating all of these outputs we get from those map component functions. That's quite straightforward. But things get a little bit more interesting if you want to map back from a reference to the target. This means we have to apply the inverse map, and the inverse map can no longer be evaluated independently, but it must be evaluated in sequence. Where we start by inverting the first map component, here in the top, which is a simple one-dimensional root finding problem with a unique solution because, again, we enforced all of these map components to be monotone in their last argument. This gives us x1, and this x1 then serves as input for the second map component's inversion, turning it again into a simple one-dimensional root finding problem, which gives us x2, and then those two outputs serve as input for the next map component's inversion, and so on. So this structure effectively means that to invert the map, all we have to solve is a sequence of one-dimensional root finding problems with unique solutions. Quite effective to do. But a very nice side effect of this dependence of each map component's inversion on the outcomes of previous blocks is that this inverse map effectively factorizes the target distribution into a product of marginal conditionals, where each of those map component functions corresponds to one term down here in the factorization. And this is very useful because, as it turns out, it allows us to sample conditionals by manipulating this inversion process. How we do this is that, well, if you have this inverse map, normally we would just evaluate it from top to bottom in sequence. But if we want to sample conditionals, we can do so by simply skipping the first few map inversion processes and replace the corresponding outputs with values of our own choosing, say x1 star and x2 star. And if we then resume this inversion process from the first map component we haven't skipped, then we of course no longer sample the true target, but we sample a conditional of the target, conditioned on those values we have provided. Because this might be a little bit abstract in this form, let's take a look at a visual example. Assume we start from a standard Gaussian reference here in 2D, and we want to map back to the target distribution. As mentioned before, we have to apply the inverse map, and we start by inverting the first map component here on the horizontal axis, which is a very simple one-dimensional root finding problem. This gives us samples from some intermediate distribution, which is some marginals from the target and some marginals still from the reference, which serves as input for the second map component's inversion, which transforms the second marginal here on the vertical axis and ultimately yields samples from the target distribution. Now, if we want to extract conditionals instead, we skip the first inversion process and replace its corresponding output x1 with values of our own choosing. For example, here I have collapsed all the x1 samples on a single numeric value on which I want to condition. And if we then apply the second inversion step, pretending that nothing is out of order, we extract samples from a conditional of a target distribution. And this is extremely useful in Bayesian inference, because at the end of the day, all that Bayes' theorem does is building joint distributions and then conditioning them. And if we can realize this operation for very non-Gaussian distributions, such as the spiral, and with triangular transit maps, then we have a very, very powerful tool for Bayesian inference. Now, despite all the advantages, there are some computational challenges for triangular transit maps. You might already have spotted some of them during this talk. Consider, for example, this triangular structure, and you might have already guessed that this might suffer from the curse of dimensionality. So the more dimensions the target distribution has, the more complex and computationally expensive these map component functions become to evaluate. For example, if capital K is 1000, then this last map component function has 1000 inputs and a corresponding number of coefficients or more. The previous one at 999 and so on. So there's an exponential increase in computational demand with dimensionality. And we also need a corresponding increase in samples to inform and optimize this map in the first place. But fortunately, there are some ways that help us alleviate this curse of dimensionality. The first one is that triangular transit maps can actually exploit conditional independence in a very natural way, which alleviates this problem quite a lot and can even turn this exponential increase in complexity into just a linear increase. We will see this on the next slide. A second very important thing in triangular transit maps is the ordering of the terms in X. This does not just control which kind of conditionals we can exploit. You remember that the conditioning trick requires us to skip past the first few map component inversions, but it can also affect the complexity of the transfer maps. We will see this in a little bit as well. To talk about conditional independence, we recall that in the triangular transit map, each of the map component functions corresponds to one term in the factorization of a target. And now in many systems, we might actually have graphical systems with a large degree of conditional independence. For example, in this Markov chain, the node x3 is conditionally independent of x2 and of x1 given x2, and the node x4 is conditional independence of x1 and x2 given x3. And if you exploit these conditional independence properties, then we could drop some conditional dependencies from those terms here in the factorization. And transfer methods make it very easy to do so by just dropping the corresponding variable dependencies from the map component functions. And this is very nice for a number of reasons. First off, it makes the map component functions simpler, numerically simpler on the one hand, but also easier to inform, which allows this kind of map to be applied even in high-dimensional systems, provided that you have sufficient conditional independence to exploit. A second advantage is for Bayesian inference, that this basically enforces this conditional structure in the graph by construction. And that's very useful for inference, because any kind of structure that we can enforce by construction is information that we don't have to learn from the graph itself, from the samples, which gives us a more robust and reliable inference routine. In exploiting conditional independence, however, the ordering of a variable still plays a large role. Assume, for example, we have a graphical system such as this one, and if we choose an ordering such as this, that's a very efficient one because it allows us to evaluate a large degree of conditional independence. Because, for example, 4 here is independent of 1 and 2, given 3, and 5 is independent of 1, 2, and 3, given 4. So we can build a very sparse map. But if we have the same graphical system and we order the nodes in a less favorable ordering, then we can only build a slightly less sparse map, which is computationally more expensive and numerically more expensive to evaluate. The ordering also affects how complicated these map component functions have to be. For example, if I have this very simple banana or crescent-shaped distribution here, if we choose a favorable ordering of this, we can actually get away with a very, very simple map, only depending on linear terms and a single quadratic term, in order to recover this target distribution exactly. However, if we flip the ordering of those states, then we actually need infinitely many basis functions in order to get an exact ordering representation of a target density. So this doesn't really affect conditional independence here, but it affects the complexity of the map component functions we have to find. Now, in many physical systems, it might actually be relatively easy to find a favorable ordering. For example, in grid-based systems, often cells that are close to each other depend more closely on each other than those which are far away from each other. But in systems in which we have no such intuition, we would like some kind of abstract methods to find a good ordering. And our colleague, Michael Brennan, for example, proposed lazy maps, which use some kind of very clever transformation, so that only the first few map component functions are nonlinear, and everything below actually is fine to be approximated with linear maps. So that's one option you can choose in such systems. And this brings us to the end of this theory section. If you have any kind of questions, please don't hesitate to send a mail to any of us or ask us in the conference venue. And now my colleague, Matt Parno, will take over with the experimental section. Thank you very much.